Applied Linguistics Group uploaded this video for BS English students. Dr. KHALID MALIK, the founder, has a PhD in Applied Linguistics TESOL. Having more than 25 research papers, he taught at many foreign universities and is now in a postdoctoral study program abroad. Join Applied Linguistics Group at youtube.com/@1966Pakistani or use a QR code to join our Facebook group at
Computational complexity. Computational complexity, a measure of the amount of computing resources, time and space, that a particular algorithm consumes when it runs. Computer scientists use mathematical measures of complexity that allow them to predict, before writing the code, how fast an algorithm will run and how much memory it will require. Such predictions are important guides for programmers implementing and selecting algorithms for real-world applications. Computational complexity is a continuum, in that some algorithms require linear time, that is, the time required increases directly with the number of items or nodes in the list, graph, or network being processed, whereas others require quadratic or even exponential time to complete, that is, the time required increases with the number of items squared or with the exponential of that number. At the far end of this continuum lie intractable problems, those whose solutions cannot be efficiently implemented. For those problems, computer scientists seek to find heuristic algorithms that can almost solve the problem and run in a reasonable amount of time. Further away still are those algorithmic problems that can be stated but are not solvable, that is, one can prove that no program can be written to solve the problem. A classic example of an unsolvable algorithmic problem is the halting problem, which states that no program can be written that can predict whether or not any other program halts after a finite number of steps. The unsolvability of the halting problem has immediate practical bearing on software development. For instance, it would be frivolous to try to develop a software tool that predicts whether another program being developed has an infinite loop in it, although having such a tool would be immensely beneficial. In computer science, the computational complexity or simply complexity of an algorithm is the amount of resources required to run it. Particular focus is given to computation time, generally measured by the number of needed elementary operations, and memory storage requirements. The complexity of a problem is the complexity of the best algorithms that allow solving the problem. The study of the complexity of explicitly given algorithms is called analysis of algorithms, while the study of the complexity of problems is called computational complexity theory. Both areas are highly related, as the complexity of an algorithm is always an upper bound on the complexity of the problem solved by this algorithm. Moreover, for designing efficient algorithms, it is often fundamental to compare the complexity of a specific algorithm to the complexity of the problem to be solved. Also, in most cases, the only thing that is known about the complexity of a problem is that it is lower than the complexity of the most efficient known algorithms. Therefore, there is a large overlap between analysis of algorithms and complexity theory. As the amount of resources required to run an algorithm generally varies with the size of the input, the complexity is typically expressed as a function n(f)(n), where n is the size of the input and f(n) is either the worst-case complexity, the maximum of the amount of resources that are needed over all inputs of size n, or the average case complexity, the average of the amount of resources over all inputs of size n. Time complexity is generally expressed as the number of required elementary operations on an input of size n, where elementary operations are assumed to take a constant amount of time on a given computer and change only by a constant factor when run on a different computer. Space complexity is generally expressed as the amount of memory required by an algorithm on an input of size n. Resources. Time. The resource that is most commonly considered is time. When complexity is used without qualification, this generally means time complexity. The usual units of time, seconds, minutes, etc., are not used in complexity theory because they are too dependent on the choice of a specific computer and on the evolution of technology. For instance, a computer today can execute an algorithm significantly faster than a computer from the 1960s. However, this is not an intrinsic feature of the algorithm, but rather a consequence of technological advances in computer hardware. Complexity theory seeks to quantify the intrinsic time requirements of algorithms, that is, the basic time constraints an algorithm would place on any computer. This is achieved by counting the number of elementary operations that are executed during the computation. These operations are assumed to take constant time, that is, not affected by the size of the input, on a given machine, and are often called steps. Bit complexity. Formally, the bit complexity refers to the number of operations on bits that are needed for running an algorithm. With most models of computation, it equals the time complexity up to a constant factor. On computers, the number of operations on machine words that are needed is also proportional to the bit complexity. So, the time complexity and the bit complexity are equivalent for realistic models of computation. Space. Another important resource is the size of computer memory that is needed for running algorithms. Communication. For the class of distributed algorithms that are commonly executed by multiple, interacting parties, the resource that is of most interest is the communication complexity. It is the necessary amount of communication between the executing parties. Others. The number of arithmetic operations is another resource that is commonly used. In this case, one talks of arithmetic complexity. If one knows an upper bound on the size of the binary representation of the numbers that occur during a computation, the time complexity is generally the product of the arithmetic complexity by a constant factor. For many algorithms, the size of the integers that are used during a computation is not bounded, and it is not realistic to consider that arithmetic operations take a constant time. Therefore, the time complexity, generally called bit complexity in this context, may be much larger than the arithmetic complexity. For example, the arithmetic complexity of the computation of the determinant of a n times n integer matrix is for the usual algorithms, Gaussian elimination. The bit complexity of the same algorithms is exponential in n, because the size of the coefficients may grow exponentially during the computation. On the other hand, if these algorithms are coupled with multi-modular arithmetic, the bit complexity may be reduced to O tilde, n4. In sorting and searching, the resource that is generally considered is the number of entry comparisons. This is generally a good measure of the time complexity if data are suitably organized. Complexity as a function of input size. Only time complexity is considered in this section, but everything applies, with slight modifications, to the complexity with respect to other resources. It is impossible to count the number of steps of an algorithm on all possible inputs. As the complexity generally increases with the size of the input, the complexity is typically expressed as a function of the size n, in bits, of the input, and therefore, the complexity is a function of n. However, the complexity of an algorithm may vary dramatically for different inputs of the same size. Therefore, several complexity functions are commonly used. The worst-case complexity is the maximum of the complexity over all inputs of size n, and the average-case complexity is the average of the complexity over all inputs of size n. This makes sense, as the number of possible inputs of a given size is finite. Generally, when complexity is used without being further specified, this is the worst-case time complexity that is considered. Asymptotic complexity. It is generally difficult to compute precisely the worst case and the average case complexity. In addition, these exact values provide little practical application, as any change of computer or of model of computation would change the complexity somewhat. Moreover, the resource use is not critical for small values of n, and this makes that, for small n, the ease of implementation is generally more interesting than a low complexity. For these reasons, one generally focuses on the behavior of the complexity for large n, that is on its asymptotic behavior when n tends to the infinity. Therefore, the complexity is generally expressed by using big O notation. Models of computation. The evaluation of the complexity relies on the choice of a model of computation, which consists in defining the basic operations that are done in a unit of time. When the model of computation is not explicitly specified, this is generally meant as being multi-tape Turing machine. Deterministic models. A deterministic model of computation is a model of computation such that the successive states of the machine, and the operations to be performed are completely determined by the preceding state. Historically, the first deterministic models were recursive functions, lambda calculus, and Turing machines. The model of random access machines, also called RAM machines, is also widely used, as a closer counterpart to real computers. When the model of computation is not specified, it is generally assumed to be a multi-tape Turing machine. For most algorithms, the time complexity is the same on multi-tape Turing machines as on RAM machines, although some care may be needed in how data is stored in memory to get this equivalence. Non-deterministic computation. In a non-deterministic model of computation, such as non-deterministic Turing machines, some choices may be done at some steps of the computation. In complexity theory, one considers all possible choices simultaneously, and the non-deterministic time complexity is the time needed when the best choices are always done. In other words, one considers that the computation is done simultaneously on as many, identical, processors as needed, and the non-deterministic computation time is the time spent by the first processor that finishes the computation. This parallelism is partly amenable to quantum computing via superposed entangled states in running specific quantum algorithms, like e.g. Shear's factorization of yet only small integers. Even when such a computation model is not realistic yet, it has theoretical importance, mostly related to the P equals NP problem, which questions the identity of the complexity classes formed by taking polynomial time and non-deterministic polynomial time as least upper bounds. Simulating an NP algorithm on a deterministic computer usually takes exponential time. A problem is in the complexity class NP, if it may be solved in polynomial time on a non-deterministic machine. A problem is NP-complete if, roughly speaking, it is in NP and is not easier than any other NP problem. Many combinatorial problems, such as the knapsack problem, the traveling salesman problem, and the Boolean satisfiability problem are NP-complete. For all these problems, the best-known algorithm has exponential complexity. If any one of these problems could be solved in polynomial time on a deterministic machine, then all NP problems could also be solved in polynomial time, and one would have P equals NP. As of 2017, it is generally conjectured that P not equal to NP, with the practical implication that the worst cases of NP problems are intrinsically difficult to solve, i.e., take longer than any reasonable time span, decades, for interesting lengths of input. Parallel and distributed computation. Parallel and distributed computing consist of splitting computation on several processors, which work simultaneously. The difference between the different models lies mainly in the way of transmitting information between processors. Typically, in parallel computing the data transmission between processors is very fast, while, in distributed computing, the data transmission is done through a network and is therefore much slower. The time needed for a computation on n processors is at least the quotient by n of the time needed by a single processor. In fact, this theoretically optimal bound can never be reached, because some subtasks cannot be parallelized, and some processors may have to wait a result from another processor. The main complexity problem is thus to design algorithms such that the product of the computation time by the number of processors is as close as possible to the time needed for the same computation on a single processor. Quantum computing. A quantum computer is a computer whose model of computation is based on quantum mechanics. The Turing thesis applies to quantum computers, that is, every problem that can be solved by a quantum computer can also be solved by a Turing machine. However, some problems may theoretically be solved with a much lower time complexity using a quantum computer rather than a classical computer. This is, for the moment, purely theoretical, as no one knows how to build an efficient quantum computer. Quantum complexity theory has been developed to study the complexity classes of problems solved using quantum computers. It is used in post-quantum cryptography, which consists of designing cryptographic protocols that are resistant to attacks by quantum computers. Problem complexity, lower bounds. The complexity of a problem is the infimum of the complexities of the algorithms that may solve the problem, including unknown algorithms. Thus the complexity of a problem is not greater than the complexity of any algorithm that solves the problems. It follows that every complexity that is expressed with big O notation is a complexity of the algorithm as well as of the corresponding problem. On the other hand, it is generally hard to obtain non-trivial lower bounds for problem complexity, and there are few methods for obtaining such lower bounds. For solving most problems, it is required to read all input data, which, normally, needs a time proportional to the size of the data. Thus, such problems have a complexity that is at least linear, that is, using big omega notation, a complexity. Use in algorithm design. Evaluating the complexity of an algorithm is an important part of algorithm design, as this gives useful information on the performance that may be expected. It is a common misconception that the evaluation of the complexity of algorithms will become less important as a result of Moore's law, which posits the exponential growth of the power of modern computers. This is wrong because this power increase allows working with large input data, big data. For example, when one wants to sort alphabetically a list of a few hundreds of entries, such as the bibliography of a book, any algorithm should work well in less than a second. On the other hand, for a list of 1 million of entries, the phone numbers of a large town, for example, the elementary algorithms that require comparisons would have to do 1 trillion of comparisons, which would need around 3 hours at the speed of 10 million of comparisons per second. On the other hand, the quicksort and merge sort require only comparisons, as average case complexity for the former, as worst case complexity for the latter. For n equals 1 million, this gives approximately 30 million comparisons, which would only take 3 seconds at 10 million comparisons per second. Thus the evaluation of the complexity may allow eliminating many inefficient algorithms before any implementation. This may also be used for tuning complex algorithms without testing all variants. By determining the most costly steps of a complex algorithm, the study of complexity allows also focusing on these steps the effort for improving the efficiency of an implementation.
Applied Linguistics Group uploaded this video for BS English students. Dr. KHALID MALIK, the founder, has a PhD in Applied Linguistics TESOL. Having more than 25 research papers, he taught at many foreign universities and is now in a postdoctoral study program abroad. Join Applied Linguistics Group at youtube.com/@1966Pakistani or use a QR code to join our Facebook group at